Hello, everyone. We are Ivan Johnson and Jocelyn Some, and we were working for our project on semantic segmentation of different prostate zones. For the overview and significance of our project, prostate cancer is one of the most common malignancies that come among men. About 1 in 8 men in the US will be diagnosed with prostate cancer in general. And Ivan and I work in a research lab where we're developing a SaaS application um, to basically track prostate cancer and enable doctors and different health professionals to seamlessly detect it. So for that project, we found that it would be beneficial to have an algorithm that could easily differentiate between the different prostate regions. So that's basically where our project idea comes from. So starting off for this project, we had to look up existing work to see if there was anything better out there. We found this one study on the segmentation of a prostate in its zones, and that basically takes ADC and T2W image slices and performs a segmentation of five different four different zones. So on the out of that study, one of the highest dice score values, which is basically a very good metric for success, was, as you see below, peripheral zone at 99%, urethra at 99%, and so on and so forth. We looked through this study and we kind of wanted to replicate it, but this study in particular did image fusion, which was out of the scope of ours. We just wanted to do a simple segmentation with the training data we were given. So for our approach, we first had to search for data sets, and we luckily found one. We found a set with 98 studies that was already segmented with labels by a student and verified by a professional. We basically took those images, we separated and used the 3D image, the 3D T2W images for validation and to create validation and training sets for our basic unit model. So we did create a unit architecture for this. And we had three models in the end. We had a basic unit, a stack unit, as well as a segResNet model, which we'll show later. So approach continued. When coding, we basically used PyTorch Lightning to create TensorBoard logs and save model training data. Then we also used it to use callbacks to save the best model during training. That way we could easily refer to the one that had the highest dice score when we're training for 1,000 epochs. We don't have to specifically try and look for one. We then wrote evaluation functions to display the predictions with Matplotlib. And out of scope, but as I said earlier, we also had multiple different models. More specifically, we had a stacked unit in which we didn't just use the T2W images, we used preprocessed ADC, DWI as well. We combined those, as well as a segResNet. So our process in general was, after building the model, was update that model, change parameters, then we retrained it on however many epochs we wanted to. We viewed the TensorBoard logs, then we evaluated the model just to see if it was as expected, and we just kept running through that loop over and over again. So with that being said, here are some of the results of our training. So this is the evaluation function for a basic unit model. On the left here, you'll see the true labels, and on the right, the predictions. They're kind of off. They're almost 90 degrees off for random reason. But our dice scores for this were 30% for the peripheral zone, 80% for the transition zone, 35.12 for the fibromuscular stroma, and 3.44 for the urethra. And those zones are just the ones that we were trying to predict. So not too great. So we decided to keep going, and we trained again a different model, the stack unit, as said earlier. And this seemed to work much better. We ended up getting 37% for the peripheral zone, and you can see the rest: 75 for transition, 33 for fibromuscular stroma, 6 for urethra. Still not amazing, but if you look at the images, at least you see like they kind of overlay for the most part. I forgot to mention that the basic unit we only use the T2W images, while for the stack unit we use all three and we stack those. Um, Finally, we made a segResNet model which outshined by far. We noticed that so the images being plotted by Matplotlib are only of the middle slice of the z-index, which is why sometimes you won't see the urethra and things like that. But we noticed that for this segResNet, we got much better data. So as you can see, the peripheral zone at 68%, transition zone at 85, urethra at 71, and stroma at 50. So yeah, this worked out much better for us in the end, compared to the unit models that we trained. So in conclusion, we had a large trial and error process. It was very much so update parameters, train model. Oh, this doesn't work. Update parameters again. But that ended up working pretty well for us. We were lucky enough to have access to a lot of computers with large GPUs, so we could train multiple models overnight for 1,000 epochs at a time. The best results were always with models that used all three ADC, 2W, and DWI data instead of just using the 2W data, and the SegResNet was obviously the best one. Yeah, we learned a lot about medical imaging data, which was a really fun project, and we'll definitely be able to successfully use this for our research. It seems pretty accurate. Thanks.
Hello, this is our supervised learning project. We're going to start off with the pre-processing. We decided to do our pre-processing before we did our model, just for ease of sharing the data and not having to write custom transforms. This pre-processing was done for our best model, which was the segResNet. This is a good visual for the segResNet. This is based on this paper, and we are using Monai's implementation of this, but we are customizing it via updating blocks and number of filters and dropout and stuff, and that such. Okay, so let's go over our model. So our model is a PyTorch Lightning model. You can see right here we can pass in all of these hyperparameters for optimizations, but this is our model definition. There are three inputs. We're taking 3D inputs with three channels. We're classifying multiple modalities, and we produce 5-channel output, which will be a 3D 5-vector image. So actually, I'll run this right here. So while we're waiting, you can see it running. Other things of note, our data is very imbalanced, and so we had to manually weight the classes. You can see our loss function takes in our class weights, which are just the inverse of the weight values or the occurrence values. Simple forward. This is us preparing the data. This is our data augmentation. Again, we're using Monai. So this is if this looks slightly different, this is just the structure needed from Monai. Here are our validation transforms. Here are some custom transforms we wrote for ourselves. Data set setting up. This is our data set. Data loaders. The other thing we did was we used the Atom optimizer with a set learning rate, but then we on learning rate plateau, so on validation loss plateau, we update the learning rate by this factor. This is our training step. We enable grad and forward the image and calculate some loss functions and save them out to TensorBoard. Same thing happens with our validation. We just log a couple more metrics on our validation step. And then on our validation epoch end, we visualize the 3D representation of our labels and models, which can be seen here. And so we produce these little GIFs. And so you can see here the different classes matching here and there. And so we also have scalars that we are tracking. So our training loss, our training TV loss, validation dice, etc. You can see which model was trained for longer. So this is our best performing model, and it was trained for 1,500 epochs, I believe. And so, yeah, other things. That's all our time. You can see it working right here. You can see us print out dice, Hasdorf, and surface distance as well. One last thing that we forgot to show in the previous video, our evaluation script, pretty simple, loading from the best checkpoint with the hyperparams as defined, and we're tracking things like per class, scores of dice, Hasdorf distance, and surface distance, as well as visualizing. If you wait just a second, you will see the images pop up. Other thing of note, we have multiple different model architectures, but they all follow the same generic structure other than the model. And so here you can see our true labels and our predictions.